Hello, everybody, and welcome back to another Teach Astronomy stream, another book club. Hopefully, you were here. Hopefully, you've been here before. If not, welcome. My name is Victoria. You probably know that already if you've been here. Oh, did I update the stream information? I just realized I probably didn't. Oh no. I always do this. There we go. Okay, it's updated now. um, Yeah, I always forget to update the stream information before we do this. But today we are not looking through a solar telescope. We did that last Friday. Today we're going to be reading the second chapter of Einstein's Monsters, a book by Professor Chris Impey, who is my boss and who you guys probably know if you've come from his Coursera courses or something like that. So if you're new to our Monday streams, we are doing a kind of like live audiobook book reading sort of thing. So every week I read a chapter or two. Last week it was just one chapter because we did a lot of intro stuff. But we'll see how long it takes us to get through chapter 2 and see if we can do 2 today or just 1, or we'll see. But every week I'm going to read a couple chapters and we're going to go through the book together. We're going to chat, going to have some fun, hang out, and at the end of it we are going to have an author's chat with Professor Impey. So yeah, it's kind of what we do around here. Welcome to everyone who's here already. I think I'm gonna wait just another minute or two before we jump on in. But while we do that, for those who are new, I guess we can just kind of recap. So Einstein's Monsters is the book. Here she is. Oh, also, if you two housekeeping things. One, if you're new, and you don't have a Twitch username yet, feel free to go make one of those before we fully start, and you can get yourself for a username, and you can chat in our little chat, and like we can talk about stuff, because I like talking to you guys. It was really fun last week getting to talk to you guys. So yeah, you just need to make one of those. It's just a email username sort of thing. But yeah, that, and also I know last week people asked if I could archive all of these book streams onto YouTube, which I'm still planning to do because they disappear here after 14 days, and since we're doing this over at least a couple months probably, that'll get annoying if the earlier parts of the book get disappear, and if you didn't catch them, we don't want you to not be able to listen to some of the chapters. So I will be doing that. That's still going to be happening. We're just trying to figure out which channel to put it on, because our team has technically 3 channels. We have Active Galactic, which is what I worked on for a long time and still am, which is like YouTube videos about astronomy education and stuff, like short ones. And then Teach Astronomy is the one where Professor Impey puts all of his Coursera courses and some like glossary definitions, I believe. And then the other one is Astronomy State of the Art, which is where we do Chris's live sessions. Well, half of them, because we've been doing half here and half there. And I'm not sure if I want to put it on Teach Astronomy or on Astronomy State of the Art. So me, Matthew, and Chris are talking about that and figuring it out. But I promise they will be up there. So if you do miss any of these, you can always go back and check those out, and then, because we want to make sure you don't have to like buy the book if you miss something or stuff like that, because it's supposed to be like a fun, free way to hang out with you guys. So yeah, I guess I will jump on in. Yeah. Let's go for it. So chapter 2. Also, I have figures this time, so we can flip over to the figures when they come up, so I don't have to struggle to hold things up to my not super great camera, which is excellent because it was not working last time. Oh, and last thing, I think there might be something weird happening with my headset. So if you guys can't hear me super well, please let me know, and I will switch microphones. I can't tell if it's just on my end where it looks like I'm quieter, but I have it like up all the way, and for some reason it's not hitting where it normally hits. So Let me know if this sounds good. If it doesn't, I can change it. So let's see. I didn't put a bookmark in here because I didn't think that far ahead, I guess. Okay, so chapter 2 is black holes from star death. Science hinges on the interplay between theory and observation. Over the millennia, humans have had many imaginative ideas about how the universe works. But without data drawn from observations, even the cleverest idea remains in the realm of speculation. Is there actually any evidence that mass can disappear from view in the universe? Despite the challenge of imagining them, black holes are real. That's the firm conclusion from nearly 50 years of research on the end states of stars. An isolated black hole is completely invisible. The rupture it creates in space-time is so small that it's undetectable with any telescope. But most stars are in binary or multiple systems, so the visible star can be a pointer to the dark companion. That's the intro section. It's short. Also, if you're here, feel free to throw in a hey in the chat if you want to. I know you might not have too much to chit-chat about. Actually, if you're here, I'm wondering if we're getting less people because it's the beginning of... Hi, I like Bossa Nova. How are you doing? I'm wondering if we're getting less people today because what's it called? Thanksgiving is coming up for Americans. People might be traveling. But let me know if you have Thanksgiving plans or if you're just hanging out, if this is a regular week for you or what. But I'm going to continue. So the next section is the forces of light and darkness. When you look at the sun, it's hard to believe you're watching a titanic battle between the forces of light and darkness. Although the sun seems barely to change from day to day or year to year, particles are careening around at near the speed of light and planet-sized parcels of plasma are constantly turning. It's a thermostatically controlled nuclear furnace. At every point within it, there is a balance between the inward force of gravity and the outward force from radiation released in the fusion of hydrogen into helium. As long as the fuel for fusion remains, neither force gains the upper hand. If you're placing a bet on the long-term outcome of this battle, gravity would be the smart choice. Nuclear fuel is finite, but gravity is eternal. After hydrogen is exhausted in stars like the sun, the interior pressure is lost, and the core of the star collapses to a hotter and denser configuration where helium can be fused into carbon. This reaction goes quickly, and when the helium is exhausted, the temperature can't rise high enough to ignite new nuclear reactions. The pressure support is lost, and the core of the star is once again faced with gravitational collapse. The sun will have a brief pyrotechnic phase as the last fuel is used up, ejecting about a third of its mass in a shell of gas moving at supersonic speed. The fast-moving gas heats up and glows, producing the gorgeous hues of a planetary nebula. Anyone watching the sun from another star system in 5 billion years will see a spectacular light show. Anyone watching from the Earth will be in a lot of trouble, since the ejected gas will vaporize the biosphere and obliterate all life. A star's life and death is governed by its mass. Oh, figure 10. It references a figure. We're gonna look at the PowerPoint. Also, hi Charlie. I always forget. I will call you Charlie from now on. I'm doing all right. I hope you're doing okay too. Okay, so figure 10. The diverse fates of stars are all preordained at birth. Depending on their masses, all stars will become either white dwarfs, neutron stars, or black holes. So we can see in this diagram here, we have the low to average mass stars turn into white dwarfs. I think this middle stage is just when they like expand and do their whole the beginning of the dying phase, I guess you would call it. But yeah, so the low to average mass star turned into a white dwarf, large mass star into a neutron star, and then very large mass star into a black hole. There we go. Let's see. Where was I? There isn't a typical mass or size for a star, although the process by which stars form from chaotic clouds of gas produces more small stars than large stars by a substantial factor. The sun is towards the lower end of the mass range, and below it are dim stars called red dwarfs. There are several hundred times as many red dwarfs as there are stars like the sun. Lifetime is also dictated by mass, since gravity determines the temperature of the core, which in turn indicates how quickly nuclear reactions will run, and therefore how long the nuclear fuel will last. A star like the sun will fuse hydrogen into helium for 10 billion years. We're halfway through that span. A star half the mass of the sun has a lifetime of 55 billion years. So no star of that mass has ever died in the history of the universe, which has only spanned 14 billion years. That's crazy. That was me interjecting. Chris did not write that. That's insane. Wow. A red dwarf, a tenth the mass of the sun, which is as puny as a star can be and still have fusion reactions, will spend its fuel like a miser. Such a star would theoretically live more than 1 trillion years, an unimaginably long time. Jesus, that's wild. Even so, the dwarf star is just delaying the inevitable because one day the fuel must be exhausted, the dim light must flicker out, and gravity will be rewarded for its patience. Stars more massive than the sun have shorter and more spectacular lives. They all do what the sun is doing now, fuse hydrogen into helium, but they have more gravity, so have hotter cores and use up their fuel at a ferocious rate. The more massive the star, the hotter its core temperature and the shorter its lifetime. Massive stars can fuse all the elements in the periodic table up to iron, the most stable element. When nuclear reactions stop at iron, the core is in a bizarre physical state. It's an iron plasma 100 times denser than water at a temperature of 1 billion degrees. Without pressure I'm not sure, it says 1 billion degrees, I'm just realizing, I don't know if that's Kelvin or Fahrenheit or Celsius. Either way, it's a lot, so. Without pressure from the core, it collapses, and the compression wave inward bounces into a multi-billion degree blast wave outward, wherein heavy elements up to uranium are fused in split seconds. This is a supernova, one of the most dramatic events in the universe. Precious metals are flung into space to become part of a next generation of stars and planets. Much of the original mass of the star is ejected, but what remains is squeezed tightly by gravity's unrelenting grip. That's that section. I'm gonna take a drink of my coffee. Who's hanging out? I feel like we had more people last time. I don't know where they went. Maybe they didn't like chapter 1. Maybe they're gonna catch it later. Alright, so next section is gravity and darkness are the final victors. The remnants of stars are truly bizarre states of matter. We have no way to create them in the lab. All we can do is use the laws of physics and hope that our theories are sturdy enough for the task. Some of the best minds in 20th century astrophysics were consumed with understanding stellar remnants. A star's aftermath depends on the mass a star has when it starts its life. Stars are born in the fragmentation and collapse of large gas clouds that produce many more low-mass stars than high-mass stars. All stars lose some fraction of their mass as they age. The processes by which this happens are complex, so boundaries between the different outcomes are not precise. Stars that start their life below 8 times the mass of the sun collapse to an unusually dense state of matter called a white dwarf. The vast majority of stars are less massive than the sun, so over 95% of all stars will end up this way. For example, the sun will shed about half its mass during its pyrotechnic late stage of life before dying as a white dwarf. The English astronomer William Herschel accidentally discovered a star called 40 Eridani, I think it's pronounced, 40 Eridani b in 1783, but he had no way to measure its size, so he didn't realize that the star was unusual. In 1910, astronomers refocused their attention on this dim star, which is in a binary system. The orbit revealed its mass to be about the same as that of the sun. They knew its distance, and deduced that it was 10,000 times. 10,000 times what? I don't know. I gotta turn the page. 10,000 times fainter than the sun would be at the same distance. Yet it was white, therefore much hotter than the sun. To see why this is puzzling, think about electric hot plates on a stove, viewed in a darkened room. One hot plate is turned on low and glows orange, like the sun. A second hot plate is turned on high and is much hotter, so it glows white. The white hot plate is much brighter than the orange hot plate. For the white hot plate to appear much fainter than the orange hot plate, it would have to be much smaller. By the same logic, the faint star in the 40 Eridani system had to be much smaller than the sun. With the same mass as the sun, it had to be much denser as well. Ernest Opic? It's like an O with the two dots on top, so I feel like it's like a long O. Ernest Opic calculated that 40 Eridani b should have a density 25,000 times higher than that of the sun, which he called impossible. Arthur Eddington, who popularized the term white dwarf, described the incredulous reaction a white dwarf produces. We learn about the stars by receiving and interpreting the messages which their light brings to us. The message, when it was decoded, ran, "I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget that you could put in a matchbox." What reply can one make to such a message? The reply most of us made in 1914 was, "Shut up, don't talk nonsense." Eddington was not a humble man. When a colleague said to him, "Professor Eddington, you must be one of the only 3 people in the world who understand relativity," he paused. So the colleague said, "Don't be so modest." Eddington replied, "On the contrary, I'm trying to think who the 3rd person is." Even though Eddington was a master of the astrophysics that predicted white dwarfs, he called them impossible stars. A typical white dwarf is the size of the Earth, but has the mass of the sun. Its density is 1,000,000 times higher than water. With no energy release from fusion, and so no outward pressure, gravity shrinks the gas, crushing the atomic structure and forming a plasma of unbound nuclei and electrons. Only at this point is gravity finally thwarted. In 1925, Wolfgang Pauli came up with the exclusion principle, which says that no 2 electrons can have exactly the same set of quantum properties. Its effect is to provide pressure that stops the stellar corpse from collapsing any further. A white dwarf will form with a temperature as hot as 100,000 Kelvin, and then steadily radiate its heat into space. Fade to black. We've seen this name before, and I have a hard time with it. Oh, hi Parzival, how you doing? I'm doing alright, reading, having a good time, hanging out with Charlie, and I think some other viewers. Hope you're doing well as well. Alright, Subrahmanyan Chandrasekhar, at the time a 19-year-old Cambridge student on an Indian government scholarship, calculated that regardless of the starting mass of a star, its white dwarf remnant can never be larger than about 1.4 times the mass of the sun. Above this mass, gravity trumps quantum mechanics and the star collapses to a singularity. The maximum mass of a white dwarf is called the Chandrasekhar limit. It was a brilliant calculation, so Chandrasekhar was understandably disappointed when Arthur Eddington, his idol, publicly ridiculed the idea of collapse to a singularity. Eddington doesn't seem like a chill guy. Chandrasekhar felt betrayed, believing that the slight was in part racially motivated. We'd like to think science is a meritocracy, but scientists can be jealous and short-sighted. Quantum pioneer Paul Dirac, who experienced similar resistance, pithily observed that science advances one funeral at a time. Chandrasekhar was eventually vindicated, and won the Nobel Prize in Physics for his insights into the structure and evolution of stars. Chandrasekhar opened the door for physicists to imagine what happens if a star collapses beyond a white dwarf. A few years later, California astronomers Walter Bade and Fritz Zwicky suggested, almost casually, that above the Chandrasekhar limit, pure neutron material might result from star collapse. But they didn't do any calculations to support the conjecture. In 1939, chain-smoking, hard-driving Robert Oppenheimer did the math. With a graduate student, he established the mass range of neutron stars. The same year, as we've already seen, he showed that with a stellar remnant above this mass range, more than 3 times the mass of the sun, a black hole must form. All stars lose mass before they die. As mentioned above, the Sun will lose half of its mass before it dies as a white dwarf. All stars beginning their lives with up to 8 times the mass of the Sun will leave behind white dwarfs with masses up to 1.4 times the mass of the Sun. If the initial mass of a star is roughly between 8 and 25 times the mass of the Sun, the core collapse continues until all the protons and electrons merge into pure neutron material. Since there's no electrical force, the neutrons jam together like eggs in an egg carton. The material is supported against further collapse by the strong nuclear force and a stronger version of the quantum force that prevents white dwarfs shrinking further. This is a neutron star, the smallest and densest type of star in the universe. Above 25 solar masses, we're faced with the prospect of Einstein's monster. That's the title of the book. That's it. It's done. Roll the credits. I'm kidding. I am going to stop there for a second, though, because these sections are a lot longer than the beginning part. So we're going to pause there, and I'm also going to show you the next figure. Woo! So, as it's been discussed, the description underneath this says, the greater the initial mass of the star, the smaller and denser the stellar remnant after all fusion is complete. The curve on the left shows the size of a white dwarf. Even though neutron stars and black holes are only a few times more massive than white dwarfs, the symbols show that they are much smaller and denser. So yeah, so we got the white dwarf, the neutron star, the black hole, the density, the size, the mass. Great. Cool stuff. How's everyone's day been? I don't know if it's either starting or ending for you guys. It's probably like, I feel like Charlie has said that they're somewhere in Europe. So you guys are probably farther into your day than I am. I know Parzival is. Parzival's done with the day. But let me know, what'd you guys do today? How's your Monday? So are these measured in Eddington scale? I think so. I don't know if they've mentioned the Eddington scale yet. I know they've mentioned Eddington. But let's see. Let me look at the Eddington scale. The figures were just for fun. I don't know if there actually is an Eddington scale. There's an Eddington number. The number of protons in the observable universe. Yeah, we're reading Einstein's Monsters by Professor Prof Impey. I keep turning things the wrong way because everything's mirrored, but there she is, Einstein Monsters. It's a fun book. Oh, Charlie's near Buffalo. Okay, nice. Talk to a musical friend. That's very nice. Yeah, we're on chapter 2 of Einstein's Monsters. So, and if you missed chapter 1, please feel free to keep hanging out. This is fun. I like having people here. But we also have chapter 1 archived in our Twitch videos. So if you want to catch up with that later. It's not super linear. It's, you know, it's a science book, so there's some linearness to it, but nonfiction is a little... Yeah, you guys can call me Vicky for sure. It's actually Vicky with a Y. I know some people put it in chat as I, but if you ever were interested. Vicky, Victoria, that science girl. I don't know if I can claim that science girl, that Twitch girl. Alright, so we will continue with this section. So, neutron stars. Neutron stars challenge the imagination. A neutron star is like a city-sized atomic nucleus with an atomic number of 10 to the 57. Its material is 1,000 trillion times denser than water. Is that 1 quadrillion? I think, I don't know. It says 1,000 trillion. A sugar cube amount of white dwarf material brought to the Earth would weigh a ton. but a sugar cube amount of neutron star material brought to the Earth would weigh as much as Mount Everest. When a star shrinks this much, the magnetic field is squeezed and concentrated too. Some neutron stars have magnetic fields a quadrillion times stronger than the Earth's. The gravity near the surface is so strong that an object falling from a height of a meter would accelerate to 3 million miles per hour at the moment of impact. Conservation of angular momentum means the normally sedate rotation of a star like the Sun is amplified when a star collapses. The fastest spinning neutron star spins 716 times per second, or 42,000 RPM. Such a rapidly spinning solid object isn't completely stable, so the solid crust can violently shift in an event called a starquake. That's really cool. It sounds very Star Trek-y, a starquake. How can a neutron star be detected? These city-sized stars should emit no light because they are not fusing elements the way normal stars do. For a couple of decades, astronomers consigned them to the category of astrophysical curiosities, something to be imagined but never witnessed. Then, in 1967, young graduate student Jocelyn Bell and her thesis advisor, Tony Hewish, detected radio pulses with a period of 1.3373 seconds from an unknown object in the constellation of Vulpecula. The pulses were so powerful and regular that Bell and Hewish thought the object might be a beacon, so they jokingly named it LGM-1 for Little Green Men. Other pulsars were soon discovered, and Bell and Hewish made the connection with the earlier prediction of neutron stars. The intense magnetic field drives radio emission from hotspots on the neutron star surface, and when the spinning neutron star sweeps the emission across a radio telescope, like a lighthouse beam, pulses are seen. People were talking. Expecto Patronum. Oh, yeah, thank you. I was like, Expecto Patronum, that's random. Yeah, this is a Harry Potter shirt. So how do astronomers separate the differences from observations? So you mean I'm not sure when you put this in the chat, but the, like, trying to figure out what's a neutron star and what's a white dwarf? Rodingen 101, is that what you meant? Quadrillion is 1,000 trillion. Yeah, okay. I don't know why he decided to put 1,000 trillion. Maybe it sounds more epic. Rodingen 101, I think, if that is what you meant, how they tell between a neutron star and a white dwarf, I believe it's something based on the well, it's the partly the radio pulses, right? So they talked about here. I don't think white dwarfs do the radio pulse at least as strong as neutron stars do, because neutron stars, they have so much, they're spinning so fast, they have so much energy. Like, I don't think white dwarfs do that. Also, for people who are new here, just as a disclaimer, I am not the astronomy expert. My boss, who wrote the book, and a couple of the guys that are on here with me normally, they're the astronomy experts. I'm the book person and the Twitch person. So I'm doing my best to answer these, and sometimes I'll have to look stuff up on YouTube, but I know some basic stuff about astronomy. But yeah, like Parzival said, they have the strong magnetic field, much stronger than anything that a white dwarf would have. So I think it's that with the certain radio emissions. Based on the radio emissions, they can determine whether it's a white dwarf or a neutron star. So yeah. There are actually some really cool things on YouTube if you search up like the sound of a neutron star. So disclaimer, they don't actually make noise, but because they're they can detect them with the radio signals, and that's how they figure out how fast they're spinning. But the radio signals aren't actually noise; they're just like a type of electromagnetic wave, just the way that like optical waves are. But people have turned these pulses into tones, and you can listen to them, and you can listen to some of the more popular or more well-known pulsars, and you can hear how fast they're spinning because every pulse is like one full rotation. So I'm pretty sure they have this one that they talked about that spins like extremely fast. I don't know what the name of it is. It's not named here, but that's a cool thing. It's fun to look at. Prof Hubble took Eye of Helix Nebula. What's the Eye of Helix Nebula? I'm gonna take a little detour. Oh, very cool. Let me show you guys the Eye of Helix Nebula. This is fun. It is spooky. Is it gonna come up? Where's my Chrome tab? Chrome, no. I don't know if this is working. Oh no. Hold on. 1 second. There we go. Okay. That's the Helix, or the Eye of Helix Nebula. That's really cool. It's very spooky. It does really look like an eye. That's crazy. Wow. Yeah. Cool stuff. All right, so we will continue. Controversy erupted 7 years later when a Nobel Prize for the discovery of pulsars was awarded to Hewish and Martin Ryle, the head of the Radio Observatory, but not to Jocelyn Bell, who made the actual discovery. Of course. It is clear to many in the scientific community that she was excluded from the honor because she was a young woman. Just over 200 scientists have won the Nobel Prize in physics, and only 2 have been women: Marie Curie in 1903 and Maria Goppert-Mayer in 1963. And also now, there was there one lady or 2 ladies that won it this year? This is another thing where the book was published in 2019, so not everything's fully completely up to date, but I'm gonna look her up. Unless someone's already put her name in the chat. Oh, Parzival, is that the pulsar thing? I think he put the pulsar thing in there. Andrea Ghez, yes. Yes, so she is the 3rd lady. Oh, does the Eye of Helix, like, scream? Is that what that says? Oh, that's very frightening. Yeah, there's some cool stuff, if you guys want to hear the sonification of some astrophysical objects, or, what am I trying to say? Some objects in space. You can look at, those links that Parvis will just drop there. Those are cool. Anyway. Surveys with radio telescopes have steadily increased the number of pulsars to over 3,000. However, the conditions that led to a hotspot are rare, so very few neutron stars are radio pulsars. The vast majority of the millions of neutron stars in the galaxy are spinning quietly in deep space, dark and undetectable. That's cool. All right. That's a section break, but I'm going to keep going because I've been chit-chatting a lot. So, all right. Finding the first black swan. It was 1964. Picture it. 1964. The Beatles took America by storm, and a brash young fighter called Cassius Clay became a heavyweight champion of the world. Science was booming as well. The term black hole appeared in print for the first time in January 1964, and in June, a small-sounding rocket launched from New Mexico identified a strong source of X-rays in the constellation of Cygnus, the Swan. Black swan is the term for those rare, unexpected events that play a disproportionate role in the development of science. It's also used by philosophers to talk about the problem of induction. Seeing many white swans is not evidence that black swans don't exist. Finding the first example of a black swan in black hole physics involved detective work that took 7 years. X-ray astronomy was a new field in the 1960s. High-energy radiation from cosmic sources can only be detected from space. The first source had been found just 2 years earlier. The 8 sources identified in the 1964 observations were consistent with supernova remnants, or hot gas created when a massive star dies violently. The Discovery observations had poor spatial resolution, so they didn't narrow down the location of the X-rays emanating from Cygnus to a region much smaller than the constellation itself. In 1970, the Uhuru X-ray satellite showed that the intensity of Cygnus X1 varied in less than a second. Astrophysicists use time as a way to measure the size of remote objects. The idea is that intensity changes cannot occur any quicker than the time it takes light to cross the source of light. The intensity variations of Cygnus X1 suggested that the object could be no larger than 100,000 kilometers across, less than a tenth of the size of the Sun. An accurate position on the sky from the National Radio Astronomy Observatory, NRAO, identified the variable X-ray source with a blue supergiant star called HDE 226868. Supergiants are hot stars, but they're incapable of emitting copious amounts of X-rays. The only explanation for the X-rays was that something in that region of space was heating gas to a temperature of millions of degrees. The decisive next step used optical techniques. In 1971, 2 groups of scientists took spectra of the blue supergiant and found periodic variations in the Doppler shift of the star that matched the variations in the X-ray emissions. Orbital calculations allowed the researchers to estimate the mass of the invisible companion that was tugging at the supergiant. The researchers speculated that a black hole was sucking gas off a companion star and that this gas was somehow heated to a temperature high enough to produce X-rays. We have a figure. Let me show you the figure. Nope. There it is. Thought I clicked the right one. So, like I just said, the researchers were speculating that a black hole was sucking gas off its companion star. So this over here is the companion star, and this is the black hole. So you can see that the material is getting sucked into this black hole, and these jets, I believe this is supposed to be a radio image. Let me check the description. I guess this is X-rays, maybe. It's kind of like an accretion disk. I guess, is it called an accretion disk if it's a black hole? I'm actually not sure. But yeah, so this is all the material that's going into the black hole, and it, I guess it is called an accretion disk. But these are the jets that are coming out, and I don't believe that these would be something that's visible, because these are radio waves, I think. So I think this is obviously like all an artist's rendition. Like this is not something we can see. Near the area of a black hole, that's the accretion disk. Okay, yeah. So this stuff. These are jets, though. So if we somehow had a view of this, I'm not sure it would look exactly like this, because this is, like I said, an artist rendering. But yeah. I like Bossa Nova gave us a Wikipedia. Yeah, so it's ionized matter. Yeah, so I believe that, because we have a video that we did on Active Galactic where we talked to a radio astronomer who looks at black hole jets, and so I'm pretty sure they are mainly visible through like radio astronomy, and like they're mostly radio waves or like X-ray kind of things. So again, artist rendering, take it with a grain of salt. Did I see stimulation animation? No, I did not. What is that? I'm going to keep reading, but let me know. Okay, let's see. I was here. Okay. As astronomer Tom Bolton prepared to present a paper on these findings at the American Astronomical Society meeting in Puerto Rico, he was racked with nerves. He was only 28 years old. 5 minutes before I gave my paper, I was revising it on the fly. I was sitting at the back of the room trying to get the latest data in my diagram, he recalled. He was also feeling the pressure of competition. He was just 1 year out of his PhD and working alone. A more experienced team at the Royal Greenwich Observatory, using a larger telescope, was getting similar data on Cygnus X1. Everyone was cautious about their interpretations, since careers had previously foundered on false claims of having detected a black hole. Within a year, Bolton was sure, and he staked his reputation on it. He next presented the research at the Institute for Advanced Study in Princeton, the academic home of Einstein and Oppenheimer. The observations were robust. The audience was convinced. The first black swan had been found. By the late 1970s, black holes had entered popular culture. Their bizarre properties fascinated people who rarely gave a thought to astronomy. Disney released a movie called The Black Hole, and its ominous theme earned it a PG rating, a first for Disney. Although the movie is low-tech and cheesy in parts, it was ambitious for its time, and it presented black holes as metaphors for death and transfiguration. The pop innocence of the Beatles evolved into ruckus rock. Rush, Queen, I love Queen, and Pink Floyd all gave nods to astrophysics. I love Queen. And that's the end of that section. BH space-time squash. What? Is that reference to what Parzival put here? Oh, yes. This is a very cool image that Parzival gave us. The animation from NASA. Oh, wrong one. It's an animation from NASA. Is it going to play? It's a GIF, so I think it's playing for you. Hopefully it's playing for you. But yeah, this thing is really cool. It just shows how a black hole alters light because of its crazy gravity. So, yeah. Cool stuff. What do you... I'm trying to figure out what you mean by BH space-time squash. Black hole space-time squash. Oh, how it like squishes space-time? Maybe? From the top view, it's a circle. Yeah. With different diameters. Gotcha. Yeah, like the, that image, it says it was like almost from the edge. So, like the one jutting out, I guess I could show it again instead of trying to, but this part that's jutting out, I believe, would be like the accretion disk that you could see. And then the black hole is, here. And this, I guess, I mean, the jets would be coming out from here and there. But yeah. It's cool. Yeah, so that's why we can see the accretion disk, because of the way that it... Yeah. Yeah, black hole, so at the center of a black hole is the singularity. So the outside of it, when it becomes black, like when the light stops, that's the event horizon, and then the very center, which is, impossible for us to see, but like there's this, where all the material we theorize goes to, that is the singularity. Yeah. Alright, so next section is weighing the invisible dance partner. Oh, Parzival said Veritasium gave a superb explanation. Yeah, Veritasium's great. He explains stuff really well. I believe we also have. I mean, Chris, I'm sure has talked about it in some of his courses. But yeah, black holes are cool. Accretion disks are interesting. Okay, so weighing the invisible dance partner. For any star, mass is density. Mass indicates the size of the star's fuel tank for fusion reactions. Mass also determines the star's gravity, so it dictates the size of a star, its internal temperature and pressure, what kind of fusion it can support, and how fast nuclear reactions occur. All this from one number. Any claim of black hole detection must be grounded in a reliable estimate of mass. Unfortunately, mass is also the hardest quantity to measure. Visual data gives brightness and surface temperature, but separate observations are required to measure distance and therefore luminosity, and then a stellar model is needed to infer mass. A solo black hole lurking in deep space has enormous mass, but it is undetectable on its own. Luckily, over half of all stars are in binary or multiple systems. Newton's law of gravity says that two objects tug on each other with equal force. They orbit a common point called the center of mass, and always stay on opposite sides of it. Imagine two people holding hands and spinning around. If they are the same weight, they will orbit a point that's midway between them. But if an adult spins a child, they'll pirouette around a point closer to the adult than to the child. More like a hammer throw, and I hope the analogy ends there, he says. That's very funny. It works the same way for stars. Two stars with equal mass orbit at equal distances from the center of mass. Two stars with equal mass orbit at equal distances from the center of the mass. I read that and it sounded strange. But if the two masses are unequal, the massive star is closer to the center of the mass, while the less massive star has a greater acceleration and travels faster in a larger orbit. And I have a figure to show you. There it is. So, like it says right here, so if this star is smaller, it looks smaller, and this star is bigger, they will not orbit perfectly around the same, like it won't be a perfect point in between the two of them. It'll be instead closer to the larger star. So the larger star has a smaller orbit around this point that they share than the smaller star. Coupling reaction or moments act opposite to each other. Same analogy? Yeah. Exactly. Okay. That's the concept. Now, let's add the math. In a circular orbit, the velocity is the circumference divided by the time taken to complete the orbit, or the period. If we measure the period and the velocity, we can get the radius of the orbit. Newton's form of Kepler's third law of motion relates the combined mass of two stars in an orbit to the size and the period of the orbit. Does that all make sense? Oh, Student McLeod, how can I get a message to Matthew? It concerns a safety issue. You can message me if you can figure out how to do the, because I talk to Matthew all the time. So if you want, I mean, you can put it here. That's fine, and I can let him know. Or if you want to send it privately, you can do a whisper, they call it, on here. Or you can just privately message me in the Discord. I think you're able to do that. But wherever's easiest for you. I provided the PDF for what? Not for this. I think Parzival provided the PDF. But yeah, let me know. I will let him know about that because we talk on a regular basis. I'll just put my message here. That's fine. All right, I'm going to continue while you do that. Sorry about that. So I'm going to repeat that last sentence because it confused me a little bit, so just to make sure everyone knows what's up. So in a circular orbit, the velocity is the circumference divided by the time taken to complete the orbit, or the period. If we measure the period and the velocity, we can get the radius of the orbit. Newton's form of Kepler's third law of motion relates the combined mass of two stars in an orbit to the size and the period of the orbit. That's 4 variables, so we need to measure 3 of them. Therefore, in a binary system with one visible star and one invisible companion, we must measure the mass of the visible star in order to nail down the mass of the dark object. How do we do that? The dance floor is dark. The woman is dressed in white. The man is dressed in black. With dim lighting from the side, the woman can be seen, but the man is invisible. They twirl across the dance floor. By the way she moves, we know the woman is in the grip of an unseen companion. Binary stars are in a similarly tight embrace and oblivious to the larger universe. If the pair of stars is widely separated and not too far from Earth, we can see both stars and simply watch their motion to measure the orbit. This is a visual binary. More often, the stars are far away, and astronomers can't see them as separate objects, but spectroscopy reveals absorption lines from each star that oscillate to longer and shorter wavelengths, representing a periodic Doppler shift caused by the orbital motion. This is a spectroscopic binary. In a binary where one star is a black hole, we have one hand tied behind our backs because the spectrum only shows absorption lines from the visible star. As with the dancers, the motion of the star that can be seen indicates the motion of the star that can't be seen. But there are 2 big complications. The first is that we need to estimate the mass of the visible star. To do this, we need to determine the distance to the binary system so as to calculate the luminosity, or the number of photons emitted by the star every second. Then these quantities, along with the surface temperature of the star, determined from its color, and its surface gravity, determined from the shape of lines on the spectrum, are fed into a sophisticated model of stellar structure and energy production to generate an estimated mass. Second, there's the problem of our perspective. Spectroscopy measures a Doppler shift, a radial motion toward or away from the observer. A binary system seen on its edge, where the orbit is perpendicular to the plane of the sky, gives the full effect, since once every orbit each star is coming directly toward us and the other star is going directly away from us. But if a binary system is seen face on, where the orbit is in the plane of the sky, no Doppler effect is measured, since all the motion is side to side. Binaries are scattered at random orientations in space, so we're faced with an additional complication in that we don't know the inclination angle. The good news is that for almost all inclination angles, the Doppler shift underestimates the orbital velocity, since usually some part of the motion is not radial. So when astronomers calculate a stellar mass, they generally can only determine its lower limit. Since the goal is to prove that the unseen companion has the minimum mass required for it to be a black hole, the method works. That's the end of that section. Alright, I think Student McLeod is still putting his message in the chat, so I will wait for that. But, oh, there it is. I was just scrolled up. Is step-down refractor, I think. Okay. That's totally fair, yes. So, if you guys saw it, yeah, Student McLeod wants to make sure that people aren't gonna get that UV radiation coming off of the translucent material screen. I'll let him know about that, because that's a good point. You probably need to, if you're looking at that, you gotta wear some sort of sunglasses or something, because you are still staring at the sun. So, yeah, I'll let him know for sure. Thank you for that. I appreciate it. I'm sure he does as well. I know we're not doing another solar observation thing this week, so he's got time to fix that and stuff for the next time we do it. But yeah. This is a long chapter. Blocking light does not equal blocking UV. Don't sunglasses block UV though? I thought they did. Yeah, right? I think so. If they have a UV protective layer, yeah. Um, yeah, so I'll make sure to let him know the next time he does that. He should have that, and have anyone else who looks at it make sure they've got some UV blocking glasses. So, alrighty. On to the next. So, black holes with gold-plated credentials. When people think about astronomy, they think of the gorgeous images taken by the Hubble Space Telescope. But many advances in understanding the universe have come from spectroscopy, the technique of dispersing light into its constituent colors. Newton used a spectrum to understand the nature of light. In the early 1800s, young Joseph von Fraunhofer survived an orphanage, a brutal overseer, and an explosion in the glass-making factory where he worked. Oh my. And went on to make the first spectrum of the sun and see features that hinted at its composition. 100 years later, a group of poorly paid women at Harvard College Observatory scanned hundreds of thousands of spectra, recorded on photographic plates, gathering information that was used to understand what stars are made of and the true size of the universe. All those ladies doing the real work, yes. Shout out to the hidden figures. I've taken thousands of spectra in my life as an astronomer, and each one is a puzzle to solve or a present to unwrap. They're key to measuring distance and chemical composition, and they yield clues to the unspeakable violence in the centers of galaxies. That squiggle on the screen at the end of a night of observation was the result of light arriving at the telescope, being smeared into a feeble streak by the spectrograph, and falling onto the silicon CCD, or charge-coupled device. A CCD converts photons into electrons, and then into an electrical signal that is processed into a map of intensity versus wavelength. One night in Hawaii, I was observing at a telescope atop the 14,000-foot dormant volcano, Mauna Kea. Data from the CCD was arrayed as horizontal streaks on the computer monitor. My eye was drawn to one particular faint streak. The dark notches in the digital spectrum were evidence of a distant galaxy made of the same elements as the Milky Way. I could infer its rotation and the kind of stars it was made of and the amount of gas mixed in amongst the stars. The red shift of the spectral features told me the galaxy was 10 billion light-years away, and the light had been traveling since long before the Earth formed. I knew that this faint galaxy had been moving away from the Milky Way faster than the speed of light when the light was emitted, thanks to the extremely fast expansion of the universe soon after the Big Bang. The universe is governed by general relativity and not special relativity, so space can expand faster than light speed. I'm slightly ashamed to admit it, but at the time I even forgot to be amazed that I could know such things about the universe. I rarely questioned the chain of reasoning and the foundation of scientific method that underpinned what I knew. Spectroscopy is the key to understanding binary stars and their orbits. It lets astronomers measure the mass of the unseen companion in a binary system. And it lets them measure the unseen mass with enough precision to conclude that Einstein's monsters are real. There are a modest number of gold-plated cases of a binary system where the unseen companion has mass sufficient to be a black hole, and they're extremely difficult to explain with any other hypothesis. Let's take a closer look at the archetype, Cygnus X1. I need a drink. Charlie said Henrietta Leavitt should get a Nobel, even though she's passed on to the happy hunting ground. I've definitely heard of her. I'm gonna check out her. We're gonna pause for a second. I'm gonna check out her Wikipedia here. Oh, she studied variable stars and Cepheids. Oh, that's very cool. That's very cool. Oh, okay. This work led her to discover the relation between the luminosity and the period of Cepheid variables. That's really cool. And she provided astronomers with the first standard candle. That's awesome. Yeah, there's a lot of ladies that did some really great stuff in not only astronomy, but in all the sciences that are often overlooked because of, sexism. But yeah. Gamer 5R6 said, "Hey, I'm not a tech guy. Can I ask for help, please?" You can. I don't know. It's okay if you don't get it. That's totally fine. If you mean uh you're not an astronomy person, that's fine. Because I don't. We're talking about like CCDs and things. But yeah, ask away. That's fine. No stupid questions. And if I don't know it, which is very possible, then we can look it up together. And while you throw your question in the chat, I'm going to continue and talk a little bit about Cygnus X1. So let's see. From the Earth, we look toward the constellation of Cygnus, riding high in the summer sky. We home in on a region near the center of the cross, marking the body of the swan. With good binoculars, we can see a blue-white star nestled in a loose group of hot young stars that all formed at the same time. 5 million years ago, when our primate ancestors split off into a branch of the evolutionary tree, these stars congealed from a collapsing cloud of dust and gas. The blue-white star of interest is 6,000 light years away, near the edge of a neighboring spiral arm in the Milky Way. That's a prodigious distance of 20,000 trillion miles. For it to be visible so easily, the star must be extremely luminous, emitting 400,000 times more energy than the sun. The light is old. It left the star when there were less than 1 million humans on the planet, and mammoths were about to go extinct in North America. We approach our prey cautiously. At the distance of the Earth from the sun, the star would be blindingly bright, 20 times the size of the sun. The width of 2 spread hands held at arm's length. Wow, that's massive. Sorry. I just figured that out. This blue supergiant is locked in a 6-day orbit with a near invisible companion closer to it than Mercury is to the sun. But the companion isn't totally dark. The blue supergiant is a ferocious fusion reactor, and it pushes a wind of plasma from its outer atmosphere into space. Some of that material is pulled in by the companion to form a swirling disk of superhot gas. At a temperature of over 1 million degrees, the gas disk emits copious ultraviolet radiation and X-rays. The companion's gravity also distorts the outer envelope of the supergiant into a teardrop shape, with its narrow end pointing toward the companion. If we could follow the pointing teardrop and approach the swirling disk that marks the companion, we would see a small jot of utter darkness at its center, the black hole. And we have another figure. Oh, no, here it is. So yes, this is an image. I think this is also an artist rendering. Yeah, it has to be an artist rendering. We got our first picture of a black hole like a few months ago. What am I talking about? Or a year ago. So this is a artist rendering of what it would look like if a black hole was sucking in a bunch of material from its binary star companion. So, yeah, cool stuff. Very similar to this one that we looked at before. Sucking in the material from the binary star that it's partnered with. Very codependent relationship. Also Gamer 5R6. Feel free to ask your question. Unless you just mean you're not understanding something here, and that was your question, and I misunderstood. But let me know. Okay. This description is inference. We've never seen this or any other black hole up close. I did get to the bottom of the last page, right? Yes, okay. Sorry. This description is inference. We've never seen this or any other black hole up close. Just kidding. We've seen a black hole now. This was written before we got the picture of the black hole. So now we have seen a black hole. I wouldn't say from up close, but we have a picture of it now, so that's cool. Still, over 100 research papers have been written on Cygnus X1. It's one of the most intensively studied objects in the sky. The orbital period has been measured with exquisite accuracy, 5.599829 days, with an error of 1/10 of a second. We need to know the supergiant's mass and the inclination of the orbit to calculate the mass of its companion. Spectroscopy and detailed modeling shows that HDE 226868 is roughly 40 times the mass of the Sun. Measuring the inclination is tougher, since the dark companion never goes behind the visible star. In other words, the system doesn't show eclipses. Recent work indicates an inclination of 27 degrees, which implies that the mass of the dark companion is 15 times the mass of the Sun. That's far beyond the maximum stellar remnant mass for a neutron star. Its gravity is so strong that the compact companion must be a black hole. All of the uncertainties in the data and all of the uncertainties in the modeling do not soften this conclusion. By 1990, the evidence was good enough for Stephen Hawking to slip into Kip Thorne's Caltech office and sign a certificate on the wall, conceding their bet. Stars massive enough to die as black holes are very rare. The Milky Way galaxy contains about 400 billion stars, most of which are dim red dwarfs far less massive than the Sun. We can use the small sample of confirmed black holes in the neighborhood of the Sun to project the total population in the entire galaxy, which yields an estimate of 300 million black holes. The few dozen gold-plated examples are a near infinitesimally small fraction of the total population, which is in turn a tiny fraction of all stars. In the past decade or so, experts have published lists of 25 to 30 gold-plated black hole candidates. The number increases slowly because of the high bar set on the evidence. All are in binary systems with extremely well-measured orbits, where the dark companions have masses more than 3 times that of the Sun, and so must be black holes. In each case, there are additional strands of evidence that support the hypothesis. The masses of these black holes range from 6 to 20 times that of the Sun, while their orbital periods range from a leisurely month to a speedy 4 hours. 2 black holes were found in the nearest neighboring galaxy to the Milky Way: the Large Magellanic Cloud, LMC X-1, and LMC X-3, both at a distance of 165,000 light-years. All the others range from 4,000 to 40,000 light-years away from Earth. Another 30 systems are waiting for more or better data to join the gold-plated list. Oh. This reading is getting to me. It's already been an hour? Jesus. Yeah, I think we might be only doing 1 chapter today, because we still got like 10 pages of this chapter with a couple figures thrown in. But yeah, I think I can only do a chapter at a time. I underestimate how long each one takes, and how much reading it makes me do, and how much my voice can handle. Gotta have some tea after this. But yeah, we'll definitely finish this chapter today. But yeah, I'm so glad everyone's here and joining me. This is so fun. This really makes me happy. This is a good time. I like reading with you guys, learning with you guys. Okay. Oh, also, this is random. This is a random question. But it is a chill session. This is our chill Monday session. When it's just me, it's chill, you know? But question for you guys. So I know that we're Twitch affiliates now, and that means that ads are put on our videos, and we also have the ability to control when that happens. We haven't tried it yet, but I was wondering if you guys are getting ads. If you get any ads in the middle, of course, Charlie. But I was wondering if you guys are getting any ads in the middle, and then it's like cutting off what I'm saying, and then it comes back and you're missing part of the reading. Because if that's happening, I want to try experimenting with like planning the ads, because we can't take them out completely. You're not getting them. Okay. Cool. Let me know if that becomes a problem, because with a stream like this, like, it could be very inconvenient if you like miss stuff, you know? But yeah, I just want to make sure that wasn't happening. Sweet. I know. Yeah, I know you should get an ad at the beginning, which is normal. And then okay. Yeah, Parzival. Parzival, you shouldn't be getting ads at all since you got a gifted sub. Um, yeah, if you're a subscriber, you don't get any ads. That's cool. You also get an emote that Parzival can probably throw in the chat there to show you. um, if you're interested. But anyway, yeah, I just want to make sure that that wasn't like causing issues. But cool. We will continue. So, next section is using gravitational optics. So far in our story, the search for black holes has depended on binary star systems, where the black hole is the invisible dancer. However, there's one method that can find the dark dancer even if it is alone. This method is based on a central prediction of general relativity, the deflection of light by any mass. Since mass bends light, a star or a galaxy can focus and magnify light from a more distant source. This phenomenon is called gravitational lensing, and was predicted soon after Einstein published his theory. It wasn't actually observed until 1979, when 2 images of a single quasar were observed. The splitting was caused by an intervening cluster of galaxies. Lensing is a subtle effect. A single star isn't massive enough to bend light much. In 1919, Eddington measured the deflection of light from a distant star passing by the edge of the sun at 2 arcseconds, a thousandth of the sun's angular diameter. Lensing is also rare. The space between stars is vast, and is unlikely that any 2 will line up closely enough for lensing to be observed. The odds of such an alignment are 1 in a million, so a million stars might have to be watched to catch one event. When a nearby star passes directly in front of a more distant star, the effect is called microlensing. With microlensing, the deflection angle is too small for image splitting to be seen, but there's gravitational amplification of the background star's light. An observer sees the background star temporarily brighten as the foreground star crosses it. The heavier the foreground star, the longer the duration of the effect. Since lensing depends on mass and not light, the temporary brightening occurs even when the foreground star or the lens emits no light. This is the only way to detect an isolated black hole. And we have a figure. Oh, somebody said they use ad blocker. That's fine. We do get revenue from ads. So maybe turn ad blocker off for a second. But also if you use it, that's okay too. Anyway, also yeah, Parzival put that little Einstein mask thing. That's what you get if you are a subscriber, and you also get you'll get access to subscriber only chats eventually when we do those. I keep saying eventually when we do those. We're gonna schedule one soon. It's just Thanksgiving has to happen first, and then we'll talk. But let me show you this figure. So this is gravitational microlensing by a black hole. So this says isolated black holes can be detected using the fact that mass bends light. If a black hole passes directly in front of a more distant star, the black hole acts as a lens, and the light of the star is briefly amplified. The image splitting is too small to be seen by any telescope. So Earth is here, chilling. If we're looking at a star, and a black hole passes in front of the star, we're going to see the light change. It's going to be bent, right? So it goes from just being a star to this microlens star and then back to a regular star. So using that and knowing that we didn't actually see anything in front of it, right? It wasn't another star that like moved in front of it the way that we were looking at it. That's pretty good evidence that there was a black hole, because something had to bend the light. And if we couldn't see it, the something, probably means it's not seeable. But yeah, microlensing. So, an upside of microlensing is that the method is simple and direct. With any binary star system, there are 2 masses to measure: an orbital inclination that's often unknown, and parameters that are derived indirectly from spectroscopy. Lensing involves a single equation that relates amplification to the mass and distance of the lens. For typical black hole masses, the amplification lasts hundreds of days, so it's easy to observe. A downside of microlensing is that amplification is a one-time event, unlike the repetitive orbit of a binary system, which allows more data to be gathered in the future. When a black hole passes in front of a more distant star, they are like ships passing in the night. The signal never repeats. More important, distance and mass are related in the lensing equation. So unless extra information is available to nail down the distance, the mass is uncertain. Hunting black holes by microlensing is a needle in a haystack activity. Microlensing surveys were developed to look for machos, or massive compact halo objects, that might explain the dark matter, which outweighs normal matter in our galaxy by a factor of 6. Machos can be any kind of object that is dark or very dim, like black holes, neutron stars, brown dwarfs, substellar objects, or free-floating planets. I can flip a page, I promise. Microlensing was unsuccessful in detecting machos, but these same surveys meant to detect dark matter did detect a few black holes. 1 in a million stars will experience microlensing, but only 1% of those will be lensed by a black hole. So several 100 million stars must be monitored to find a couple of black holes. A Polish research group used a decade of data from a 1.3 meter telescope to sift 3 good black hole candidates from billions of photometric measurements for 150 million stars. Now that is dedication. That's the end of that section. Parzival, what did you put in here? Oh, amazing. Just finding all these amazing animations for me. Thank you. I will show you guys. Parzival found an animation of, keep clicking the wrong one, of the gravitational lensing. So this is very cool. See that light is being bent, so it distorts things as the black hole moves through. So that's how scientists can tell that there's probably a black hole there. Oh, I'm glad you enjoy my commentary. I like commenting on things, you know? That's why we're doing book club, or else I'd just be reading this by myself and just like laughing every once in a while. All right. Physics at the Edge of the Maelstrom. The narrator of Edgar Allan Poe's 1841 short story, A Descent into the Maelstrom, is a young man who ages suddenly as he anticipates his likely demise in a whirlpool off of the coast of Norway. One of his brothers dies in the abyss. Another is driven insane by the spectacle. The narrator alone survives to tell the tale. He winces as he recalls the scene. Quote, "The edge of the whirl was represented by a broad belt of gleaming spray, but no particle of this slipped into the mouth of the terrific funnel, whose interior, as far as the eye could fathom it, was a smooth, shining, and jet-black wall of water." Unquote. Poe's fictional narrator found a strange and terrible beauty in the maelstrom. We might feel similarly about a black hole. Einstein's monsters are terrifying, but riveting. Like the gleaming spray and flotsam and jetsam at the edge of the maelstrom, a black hole in a binary system gives rise to spectacular effects. It's a wonderful irony of astronomy that objects which are in principle totally invisible can be the brightest objects in the universe. The reason is gravity. For a terrestrial example, consider the Itapu? I think it's Itapu Dam at the border between Brazil and Paraguay. This facility generates a phenomenal amount of power, 100 terawatt hours per year, enough to fulfill the energy needs of several 100 million people. Where does this power come from? The dam creates an elevated body of water from the Parana River. Every second, 300,000 cubic meters of water falls 110 meters, converting gravitational potential energy to kinetic energy as it accelerates to 100 miles per hour. The water is slowed down to 10 miles per hour at the bottom of the dam as kinetic energy is turned into rotational energy by turbine blades. The spinning turbine generates electricity. In a similar way, matter falling into a black hole generates energy. Let's look at what happens when matter falls into a black hole. This process is called accretion. Black holes mostly attract the hydrogen gas that forms stars and loosely fills the empty space between them. These protons and electrons could fall straight in. They could plunge toward the event horizon, disappear into the black hole, and never be seen again. However, that's very unlikely, because few gas particles will be heading directly toward the black hole. Most of them will have a sideways motion. With some sideways motion, the particles might head into space, never to return, or they might start orbiting the black hole. They'll also collide with one another, since they have slightly different trajectories. So particles take an indirect, chaotic route towards the black hole, and with all the collisions, the gas gets hot. Now we add the crucial fact that the black hole spins, which gives it angular momentum. In physics, angular momentum is always conserved. There's a rule about how particles move in a rotating system. The black hole spins quickly because it has collapsed and is small. A slowly spinning massive star will turn into a rapidly spinning stellar remnant. Think of a skater spinning slowly when their arms are spread out, then faster as they bring their arms in to be more compact. The spinning black hole swirls the hot gas around it, just as water near the edge of a bathtub would swirl if you vigorously stirred the water at the center. The swirling of the gas is strongest around the black hole's equator. This vortex of hot gas is called an accretion disk. That's what we were talking about before! Accretion disks! Very cool. Since most of the gas is concentrated in an accretion disk around the black hole's equator, the regions above the poles of the black hole are relatively empty. That means some of the hot gas can escape along the poles. As it does so, it converts spin energy from the black hole into kinetic energy. That gas is ejected in twin jets of fast-moving particles that are aligned with the spin axis of the black hole. Those jets carry away a small portion of the gravitational energy of the matter that's falling in. If we could get close to the accretion disk, we would see bizarre distortions due to the black hole's intense gravity bending light. There's a figure. Here it is. Bam. So this is an image from a computer simulation of a black hole and surrounding accretion disk using the full equations of general relativity. So the brighter left side of the disk is approaching and the darker right side is receding, and the distortions are caused by mass bending light. Very, very cool. My throat is starting to get a little scratchy. Just a few more pages. We can do this. We can do this together. I'm having a really good time. It's just that you start feeling it a little bit. Your vocal cords start getting a little tired. That's okay. Alright, so we can visualize the swirling disk of gas, just like the flotsam and jetsam at the edge of Poe's maelstrom. The center of the action is a spinning black hole, dark and implacable. As particles get closer to the black hole, they move faster. Their gravitational energy is being converted into kinetic energy. They're also colliding, so the gas heats up, and friction within the disk causes intense thermal radiation. Gas in an accretion disk has a temperature of millions of degrees and glows brightly in X-rays. Thus, gravity power is turned into radiation. There's irony in the fact that something so black can create a scene that's so bright. The process is extremely efficient. Efficiency in this context refers to the fraction of stored energy that is converted into radiation. Chemical burning, the source of most of our power on Earth, has an efficiency of 0.0000001%. I want to make sure I got the right amount of zeros. Stellar fusion, the process that makes stars shine, has an efficiency of just under 1%. Accretion onto a stationary black hole has an efficiency of 10%, increasing to 40% for a spinning black hole. Black holes are the most powerful energy sources in nature. Yes. 6 zeros. Crazy. Yeah, so so the way that we make like burning coal and oil and stuff like that has an efficiency of 0.0000001%. Black holes have 40%. That's crazy. All right. Gas doesn't fall easily into the black hole because it has angular momentum. The same is true for planets orbiting a sun. Working out the details of black hole accretion was one of the most challenging problems in astrophysics. It took dozens of researchers nearly 2 decades to solve. Gas particles in the disk experience friction, so the entire disk acts as if it's viscous. As a result, some material loses angular momentum and moves closer to the black hole, while some material gains angular momentum and moves farther out. Particles that get close to the disk's inner edge are moving within a hair's breadth of the speed of light. As it approaches the event horizon, a typical particle experiences a slow spiraling in through the accretion disk, jostling with all the other particles. Then, at the inner edge of the accretion disk, gravity pulls it directly into the black hole. A black hole gathers mass through this sequence of events. The limit to accretion was calculated by Sir Arthur Eddington early in the 20th century. The Eddington limit assumes a spherical geometry and asks at what point the gravitational force pulling a particle inward is matched by the radiation pressure pushing the particle outward. The maximum rate at which mass can be added to a black hole is rather low. In a year, it can grow by no more than a third of the moon's mass. At that rate, it would take 30 million years to double in mass. But the efficient conversion of mass falling into radiation going out But the efficient conversion of mass falling in to radiation going out means the black hole is blindingly bright. A black hole fueled by gas from a companion can be 100 times brighter than a star of the same mass. Oh, and that's the end of that section. Great. Yeah, Eddington limit, yeah. That must have been what you were talking about before. Oh yeah, and there's a nice simple English Wikipedia article about relativistic jets that explains them nicely. Thank you for that, Charlie. Also, I don't know if I need a jug of coffee. The coffee is just to like wake me up a little bit because it was a little early today. But I totally forgot to get water. So that's probably why. But it's okay. I'll drink a lot later. I'll drink a lot of water after this is done. And then I have a week to rest my voice. Okay. So I think this is the last section for this chapter. Yes, and we have one more figure. Very exciting. So let's finish this off. A tour of the binary star bestiary. A low percentage of stars end their lives as neutron stars, and the percentage that end their lives as black holes is even lower, a few tenths of a percent. Black holes are as rare as black swans. To repeat, the distribution of the masses of stars as they form is highly skewed toward low-mass stars, and there are hundreds of low-mass red dwarfs for every sun-like star. Red dwarfs die as fading embers called white dwarfs. Therefore, over 95% of all stars will end their lives as white dwarfs rather than as neutron stars or black holes. Just over half of all stars are single, like our sun, while a third are binary and 10% are in systems with 3 or more members. Most binaries are in wide separation orbits with periods of years or decades or even centuries, so they don't interact and affect each other's evolution. A small fraction of binaries, less than 5% of the total, have orbital periods of between several hours and several weeks. Any star has an imaginary boundary within which all material is gravitationally bound to it. For an isolated star, this boundary is a sphere. When binary stars are close together, these boundaries are stretched into teardrop shapes with the points touching. Mass can flow from one star to the other through the point where the teardrops connect. Typically, the higher mass star will siphon gas off the lower mass star. If they are really close together, the imaginary surfaces merge into a common envelope, and mass can move easily between the stars. Most close binaries will contain 2 red dwarfs, since most stars are dwarfs. When these stars die, they collapse into white dwarfs, but low-mass stars live for so long that most of them have not died yet. High-mass stars have short lives, so if we locate binaries with a high-mass star and a low-mass star, it's likely that the more massive star will have died and left behind a neutron star or a black hole. These are the types of stellar remnant binaries in order of increasing scarcity. Double white dwarf and neutron star, white dwarf and black hole, double neutron star and black hole, and double black hole. Let's call this last one the double black pearl. It's the rarest combination of all. We'll return to it later. To tell all the stories of binary stars would require a book far longer than this one. Like the relationships between people, they're hugely varied. Couples can be large and small, and personalities can be hot and cold. There's give and take on both sides, and one life profoundly affects the other. Sometimes one partner leaves the relationship, and one partner almost always dies before the other. With stars, a close relationship can even lead to life after death. Consider two normal stars orbiting each other in the prime of life, fusing hydrogen into helium. The more massive star exhausts its hydrogen first and bloats into a red giant, spilling gas onto its companion. With both stars engulfed in gas, they spiral closer to each other. The more massive star dies, collapsing into a white dwarf. Eventually, the less massive star ages and swells, pouring gas onto its dead companion. The very strong gravity of the white dwarf compresses the gas sufficiently to ignite fusion, and it flares briefly back to life. This is called a nova, or new star. The violent fusion ejects much of the gas, and the process can repeat episodically. Sometimes a nova takes a star from a faint glow in the telescope to naked eye visibility. If the mass transfer is large enough, the white dwarf can be pushed over the Chandrasekhar limit of 1.4 times the mass of the Sun. In this case, the dead star dies for a second time as a supernova, leaving behind a neutron star. Here's the life story of a binary that ends up with a black hole. Two hot, massive stars live in a tight binary orbit. The more massive star exhausts the hydrogen in its core and expands, shedding most of its envelope onto its companion, leaving behind a naked helium core. After a few 100,000 years, it dies violently as a supernova that leaves behind a black hole. The less massive companion gains gas from the explosion, which accelerates its evolution. After 10,000 years, it expands as it reaches the end of its life, spilling gas onto the black hole and triggering an intense X-ray emission. Then it too detonates as a supernova and, depending on its mass, the final system includes either a neutron star and a black hole, or a double black hole. It can die 2 times. So let me show you the figure. So essentially what Professor Impey is saying here is that when stars die, if they're in binary systems, if they die and they're in a binary system, say this one dies, right? It turns into a white dwarf, and then this one's still alive, and then this one dies, and it does its thing and like propels gas into the air. This one could pick up some of that gas because its gravity is more intense now that it's a dead star, and it can actually like reignite the fusion in it if it has enough gas and like material and stuff, and then almost like it could like continue like that, I think for a while, which is really crazy. But yeah. And then we have this figure here that I put on the screen for a second. So this is the evolutionary sequence that led to a rare binary black hole system. So at the top left, it starts as, they call it ZAMS, and that's zero age main sequence. Then the more massive star spills material onto its companion. So that's this. I'm pointing at the wrong thing. So this is zero age main sequence. That's when they first start out, and then the more massive star spills material onto its companion by Roche lobe overflow. So it's spilling that material on, or yeah, like that way, and then Yeah, and so nova and supernova are different things. But the a nova, according to this book, so when a white dwarf compresses gas sufficiently enough to ignite fusion, it can flare briefly back to life, and it's called nova or a new star. Yeah, so like Student McLeod said, you can nova repeatedly. And it seems like it'll give it like a second life almost. Yeah. And then, so back to this figure. So this is the Roche-Lobe overflow. And then the next one is after some time in a wolf riot phase, the more massive star dies as a supernova. So that's supernova. And then it becomes a black hole. So there's a black hole, and that's a regular star. And then it emits X-rays as a high mass X-ray binary right here. And then we go back up here. The two stars then occupy a common envelope. So this is the common envelope. Then the second star dies similarly, becomes a supernova, both black holes, and then they merge into a gigantic black hole. So yeah, so this is essentially like you got two stars, one dies, they kind of combine due to the way that because of their closeness, and become an X-ray binary. Yeah, and then the other one, when the other one dies, becomes a black hole. And this is, again, like extremely rare because they both have to be like huge stars to start out with. So as Professor Impey said in the book, this is the rarest combination of binary stars. Usually you'll see a black hole with something else that's either alive or maybe a dead neutron star or a white dwarf or something like that. So yeah. Just another paragraph or so. So, black holes are a bizarre but inevitable consequence of the evolution of massive stars. If they are in binary systems, their interaction allows them to be detected. Every second, somewhere in the universe, a massive star dies violently. Every second, a patch of space-time is pinched off from view, and every second, a black hole is born. But what if there was another way to form a black hole? And what if the result was even more monstrous than anything previously imagined? And that leaves us at the end of chapter 2. And chapter 3 is about supermassive black holes. Ooh. Exciting. Then LIGO picks up the gravitational signal from the merger. Yeah, that's what LIGO's there for. And then a larger black hole is just a few tens of stellar masses in total, most likely. I think, how big does a star have to be to become a black hole? We're gonna learn today with Wikipedia. I'm trying to find the lower limit of a black hole. Gosh. Does anybody know what it is? The Kindle version is $9.99 of this book. That's very possible. I know there is a Kindle version of this book. If the supergiant's mass is greater than 3 solar masses, it can become a black hole. Okay. Yeah, I don't think it actually is too much, but the way it condenses, I mean, the whole thing is like the density of the black hole is the big deal, right? Because it turns into a very, very small thing, and 1.4 solar mass. Yes. And it'll continue to get more massive because of the accretion disk, I believe. Again, I am not the is that for supernovae 1A? Let me look up. Yeah, the Chandrasekhar. Hold on. We're gonna learn together. Oh, the Chandrasekhar limit is yeah. So 1.4 times mass of the sun. Anything less than that will stay a white dwarf forever, and that's most stars. Anything above 1.4 is going to be either a neutron star or a black hole, depending on how much bigger it is after that. Bro, do you know the fact that you can become a black hole if you're pressed to the size of less than an atom? Yeah, like, I mean, all that stuff of, I mean, I don't know how that would happen, but like, yeah, the idea of a black hole is just like pressing stuff down so much that like the density becomes that you would need to make a black hole, you know? Like there's I forget what it is, but people say like, oh yeah, if you compressed all of Earth down into a certain amount, it would become a black hole. I can't remember exactly like what the size of it is, but it's pretty small. I think it's like a palm of your hand, something like that. The Schwarzschild radius, yes. Yeah, I'm just trying. I'm just learning along with you guys. Oh, it's 9 millimeters for Earth, and then it's 3 kilometers for the sun. Okay, yeah, that tracks. That tracks. So 9 meters or millimeters. I think I have a ruler in here. This is centimeters. So 9 millimeters is what, less than or so it's right. Of course, I picked the clear ruler, but here, that helps. But you can see that there to there is only 1 centimeter. So if you put Earth into like this, about, it's like the size of like your nail on your finger, like your pinky finger, then it would turn into a black hole. That's a lot of mass that needs to condense a whole lot, of course. But it's cool. The black hole limit is somewhere around 2.3 mass of the sun. Yeah, I think it's around there. But yeah, it would instantly evaporate. Yeah, I don't know. I mean, obviously, all the like ideas of like the black hole, like crunch this thing down to this small, and then it'll be a black hole. Like all of that's theoretical. I don't think you could do that anyway with anything here. But 2.4 to 3 solar mass is the region of uncertainty. Gotcha. Okay, yeah. So that's the part where it's like maybe it'll become a black hole, maybe it'll be a neutron star, depending on how it, like how much gas is surrounding it and stuff, how it explodes, things like that. And also like since we haven't really been able to observe a super huge amount of black holes, there's always that uncertainty. But yeah. All right. I think that's pretty much it for today. Yeah, because that takes us to the end of chapter 2. Unless anybody has some last minute questions, but I'll do our wrap up stuff. So again, just quick reminder, if you haven't yet, please follow us. Then you'll get notifications for the did I read it fast? It's been like an hour and 45 minutes, man. It felt like a long time. I thought I would get through 2 chapters today, but it was a lot. But yeah, I'll definitely pass that on to Matthew, Student McLeod, for sure. But yeah, so if you haven't yet, please follow us. You'll get notifications when we go live, so you won't miss any of these. And hopefully Twitch will actually give you notifications. It's been doing it for me, so hopefully it'll start doing things for you guys, doing the same, doing it at the right time for you guys, because I know some people are having issues with that. If you haven't yet, we also, if you'd like Discord, we have also got a Discord group for the entire Teach Astronomy channel. It's called Astropedia, and I can link that in here because I still haven't figured out how to put it on our on our about page because it doesn't like trying to set that up for me. Also, as I said before, we are affiliates now, which is very exciting. And if you want to help support our channel, you know, we used to be grant run, the entire Prof Impey group, but we have since lost our grant funding. So we just want to keep trying to bring cool astronomy content to people. I know we have a couple subscribers already, and I really appreciate them. I'm actually going to shout them out. I don't know if they're here, but I figured we haven't done that before. I know Parzival has a gifted sub, which is super cool, from another subscriber called Mick. And if I could find this, that would be amazing. I don't know if people are actually here, so I feel like shouting them out doesn't really... But we appreciate them, is what I'm saying. And if you wanted to support us, that would be really awesome too. And like I said, you get little emotes, and you'll get access to chat in subscriber-only chats eventually when we have those. And it'll go towards a good cause of like making sure that we can keep bringing this stuff to you guys. After that, so next streams will be, obviously I'll be doing this next Monday, and on Wednesday this week, Professor Impey is going to have a Q&A session here, so make sure you are here for that. I believe it's at 10 a.m. my time, which means the same time that we started today. I'm going to put that on schedule. And yeah, you can come ask all your questions and stuff. And then we will be taking a break for the rest of the week because of Thanksgiving here in the U.S., and we'll be back, like I said, on Monday with our regular schedule, and I'll be here for book club. Oh, and high altitude Cherenkov, I just saw your comment of like, yeah, the super big stars can't make super massive black holes. Yeah, that makes sense. I think it's just the supermassive black holes have to be like combinations of stars, the way that like the binary black hole system would merge, I think. But yeah, I'm glad you guys enjoyed it. I'm glad you could hang around. Anyone have anyone that we could raid? So we can go send you guys over. I don't know who's on right now. Let's see. Is CosmoQuest on? We'll go raid CosmoQuest. But yeah, everybody have a good rest of your week. I'll kind of see you on Wednesday. I'll be in the background, you know, running the stream. But you'll mostly see Professor Impey, and you'll hear Matthew. And I will see you guys on Monday. Thank you so much for joining. And we're gonna raid CosmoQuest. They playing Minecraft? It says Minecraft. I'm not sure. We'll see. But go enjoy that, and I'll see you guys next time. Have a good week, or have a good week. I was gonna say weekend. Have a good week. Bye, guys.